Hello, this is the ChemDoctor signing on, and we are at the beginning of another year, and you may find yourself in a high school chemistry class or an advanced placement chemistry class or university level general chemistry. And in the beginning of those courses, almost always the professor or the teacher will start by talking about atomic mass. So if you look at the periodic table, and I'm just going to grab a square here, and we'll look at carbon because I don't know, I always pick on carbon. And you'll notice that off the periodic table that there are basically two numbers associated with a particular element in the box. The top number is the atomic number of the element. Usually it's a top number. Alright, and the atomic number, which is not really the subject of this video, tells you the number of protons for that particular element, which is a fixed value. This bottom number, which happens to be the subject of this video, is what we call the atomic mass. Alright, and atomic mass is an important concept in chemistry because later on, for example, we're going to need to be able to mass a particular element out on a scale or mass a particular molecule out on a scale in order to carry out chemical reactions and things like that. Other applications might involve something like a Mars lander, for example, taking samples, soil samples, and then determining what elements are present within that sample. All of this boils down to, or at least one of the identifying factors of an element is its mass. So how do we determine the mass of an element or the mass of a molecule? And that's the subject of this video, right? We're going to talk about how a mass spectrometer works, and this is an instrument that measures the mass and numbers. Let me get that a little bit better. The numbers, the mass and numbers of a particular element or molecule. Mass and numbers. So the mass and how many of a particular type of element. Alright, so how does this thing work? On the screen what I've done is I've given you a loose schematic of what one of these instruments looks like. And you can go on the internet and Google mass spectrometer and you're going to get the phone book of images. And what I tried to do here was draw you a picture of one that's been boiled down into as simple of a diagram as I can get to. So how does this thing work? Alright, first thing is we're going to inject a sample into the instrument. What is the sample going to be composed of? Alright, now here's the thing about this. Alright, this instrument can be used to determine the mass of a particular element, and it can be used to determine the mass of molecules. Alright, so the number one thing is we can determine the mass of elements, of a specific element or atom. Alright, and we can also determine the mass of molecules. And remember the difference between an element and a molecule. An element is an atom of all one type. Alright, an atom of all one type. So we might, for example, be looking at the mass of a sample of carbon atoms. Alright, and in the case of a molecule, you're dealing here with a collection of atoms. A collection of atoms bonded in a specific ratio. Bonded together in a specific ratio. Alright? Now, how's this going to work? The first thing is that the sample is going to have to be converted into a gas. Alright? Now, in most of the explanations you see about this in textbooks or on the internet is they're going to say that the sample has to be vaporized. Alright? Which is a fancy way of saying that we've got to convert the material into a gas. So the thing that you got to remember about this, all right, is you got to go back to your basic understanding of chemistry. And remember that any kind of substance is going to have what we call different phases. So they can be in the solid phase, the liquid phase, or the gas phase. And how we get from the solid to the liquid to the gas phase or the gas state for any kind of substance usually is by heating it up, all right? So what you're going to do to vaporize the sample is once it's injected into the instrument is there's going to be some kind of heating element or some kind of apparatus in here that's going to take and convert whatever you put in there from the solid form into the liquid form into the gas. If you're still confused about this, think of an ice cube. All right, and if you pull an ice cube out of the freezer and you start to heat it up, it's going to melt and become a liquid, right? It's going to be messy all over the counter, and if you continue to heat it, you're going to convert this material into steam, right? In the case of water, which is now in the gas phase, and if you wanted to, could be injected into this instrument so you could determine the mass of an H2O molecule, for example. That's just an example of how we could use this. All right, so the sample is going to be injected into the instrument where it's going to be converted into a gas by heating it. All right, the gas is going to be transferred along a column, and you can think about this as the gas being transferred down a hallway, and it's going to pass through a region where there is going to be a beam of electrons that are being projected perpendicular to the stream of gas particles that are traveling along here. All right, now this electron beam you can think of being basically a beam of atomic bullets. Now you imagine yourself walking down a hallway and you're going to pass by a doorway where somebody's got a 50mm machine gun shooting bullets directly across the hallway. And what's going to happen as you walk through that stream of bullets is you're going to be hit by some of them. And the situation is going to get really messy. You know, bits of flesh are going to come flying off you. Now, if you imagine this situation on an atomic level, and let's say you happen to be a carbon atom, all right, that's been projected through this beam, what's going to happen as these electrons impinge on you or hit you is some of the electrons that you have within your particle are going to be knocked free. And once that happens, the carbon is going to be converted into an ion, specifically into a positively charged ion. So a way of looking at this is that you've got carbon, and remember what I said at the beginning of this, because the carbon has 6 protons in it, the neutral atom is also going to have 6 electrons. So as this carbon, which has 6 electrons, is hit by this electron beam, all right, which I can show this way, some of those electrons, at least usually 1 electron, is going to be knocked off of the atom. And the result is that you're going to have an atom now that will still have the same number of protons it had going into this. But now it's going to have 1 less electron. So a way of looking at this would be like this. We're going to have 6 protons here, but now there's going to only be 5 electrons. And the atom now is going to have a charge literally of +1 on it. The interior of the instrument at this point in this narrow hallway carries a positive voltage, all right, a positive voltage. So what's going to happen now once this particle has got a positive charge on it is it's going to be accelerated down the hallway. The reason being is because now the particle has the same charge on it as the voltage in the hallway. All right? Remember your physics, because anytime you've got 2 charges that are the same, all right, those charges are mutually repulsed from one another. So once the particle, and this holds for the molecules as well, once the molecule or once the atom has a positive charge on it, it's going to be repulsed and accelerated down this hallway. All right, accelerated down the hallway, which is another way of saying that it's going to be sped up, made to go faster. Now, in addition to the fact that it's going to be made to go fast and it's got a positive charge on it, the beam of particle is going to be narrowed by progressively shooting it through a series of slits. So when it exits at this point right here, as it moves down this hallway, it's going to be projected into a very narrow beam of particles, all right? Into a very narrow beam of particles. So this thing, so in a way, you're shooting it down a rifle barrel, is my point. And think about a rifle barrel. The barrel itself only has room for one bullet as the bullet moves down the barrel. So these particles have been converted into a positive charge. They're sped up, and the beam is narrowed down as if you're shooting the positively charged particle through the barrel of a rifle, for example. Now, the particle is going to reach a place in the instrument where there is a magnet, and I'm gonna show it like this. The magnet is generating a magnetic force which is set up to repulse this positive particle. All right, now think about magnets for a minute. I'm going to draw your attention up here. All right, they have, you can think of a magnet this way. There's a positive head and a negative head. And if you set the two magnets, if you set two magnets next to one another with their heads reversed, then the magnetic forces are attractive and the two magnets stick together. On the other hand, if you set up the magnets so that the heads are the same, like this, then the two magnets are going to repulse one another. All right, the magnetic forces are going to force the two magnets apart. And that's what we have going on here. So the magnetic force is set up so that it repulses the positively charged particle. And I'm going to show that with the blue arrows perpendicular like this. So the result is that the particle is going to be deflected. All right, and here's the main point of this instrument. The magnetic field is going to be adjusted in this experiment so that this particle is deflected in such a way that it will hit the detector in a specific location. All right, so we're going to adjust the voltage so that the particle will be deflected so that it's going to hit the deflector in a specific location. So the magnetic field, I want to abbreviate this, it's going to be proportional to the mass of the particle. It's going to be proportional to the mass of the particle. So how we set up an experiment like this is that we're going to inject a standard in here in order to be able to tie a certain magnetic field to a certain mass. And the standard we're going to use is going to be C12. All right, and remember that C12, we know its specific mass because it's going to have 6 protons in it, and it will also have 6 neutrons. And what you need to remember about this is that the number of protons and the number of neutrons determine exactly the mass of a particular element. So we're going to use C12 as our standard here. So we inject C12 into the instrument. We ionize it by hitting it with electrons. It's accelerated down the hallway by utilizing a voltage which is the same charge as the particle. The beam is narrowed down into a singular beam. We then hit it with the magnetic field to deflect the particle. The magnetic field is adjusted so that the particle is going to hit the detector in a specific location. So we can literally tie a specific magnetic force to a specific mass. All right, and then that leaves us with the detector then, and the second part of this, which is counting the particles. So how does this work? So then we have, on this end of it, we have these positively charged particles that are hitting a plate. And when they hit the plate, the particle is going to be neutralized by donating electrons to it. All right, and the thing that you've got to remember about moving electrons. So we're going to donate an electron from the plate on the detector to the charged particle to neutralize it. So we're going to give an electron back to the particle. All right. Now here's the catch to this. The movement of electrons generates an electrical current. All right. Now, the electrical current is proportional to the numbers of particles. So the smaller the current, the fewer the particles. The larger the current, the more particles you've got. So we can tie the amount of electrical current, the charge to mass ratio, to the number of particles. So let me actually add that in here. So charge to mass ratio. So we have two issues then with the mass spectrometer. We can precisely determine the mass of a particle, and we can know how many particles are hitting the detector. All right, because we know the mass and we know the amount of current that's produced at the detector, and from that we can determine a charge to mass ratio, which allows us to determine how many particles are hitting the plate. Now, let me take this one step further. So we use a standard to calibrate the instrument, usually C12, because we know precisely what its mass is. So then we can come back and we can inject an unknown in here. All right? The unknown is going to be converted into a charged particle. Its charged particle is going to be narrowed down into a singular beam. We adjust the magnetic field so that the unknown particle is hitting the detector in a specific location. We know the current that is being generated at the detector, so we can determine a charge to mass ratio. We compare that charge to mass ratio to the charge to mass ratio that was determined for the standard, and we therefore can then determine, actually a computer does this for us, we can then determine the mass of the unknown, and we can know how many of those particular particles were in the unknown sample. And with that, I'm going to go ahead and close the presentation.